Alex. I'm the CEO and co-founder at Netris. Before Netris, I've been in network engineering many years. And I guess between all of us in this room, we probably have thousands of years of network engineering background collectively. And what we do at Netris, we work with neoclouds, AI factory operators. We help organizations deploy large GPU clusters between, anywhere between 1,000 to 40, 50,000 GPUs, anywhere between few hundreds to many thousands of switches in every cluster. And networking is quite different in AI compared to traditional data center networking. And my today's presentation is about that. So we're Netris. We're a network automation, abstraction, and multi-tenancy company. We call this NAAM. NAAM is a term we invented, and NAAM is what comes after SDNs and intent-based networking. And that's because when you're building AI infrastructure, networking for AI infrastructure, for hosting lots of GPUs, you have different networking requirements, and you cannot use SDNs because everything in software, and you're pushing lots of traffic, and you cannot use traditional, fabric managers or intent-based networking technologies because managing the switch fabric is not enough. And I'll walk you through more details. One close example of NAAM that we all have seen, other than what we do at Netris, is basically what large hyperscaler cloud providers, they build and are running under the hood. The technology that we've created is something similar, but it is more designed for AI cloud operators. We're blessed to work with a lot of them, and I'll tell about all that experience. But before that, before we proceed to AI and our recent success in that space, I wanted to talk just a little bit about our pre-AI customers. So these logos you see on my slide, these are our traditional data center customers before AI. And these are organizations who were hosting many switches for whatever reasons. They needed to be on-prem, and they needed dynamic network configuration for their infrastructure. So they were basically building private cloud. So we worked with these amazing customers, and this is where our technology evolved. And when we entered the space of AI, which for our company happened roughly a year and a half ago, we got tremendous traction. And it's been roughly a year when we became first NVIDIA-validated network automation vendor. And since then, we've been working with lots of AI operators. Over the last 12 months, we basically launched more AI clusters than entire networking industry combined. And I'll tell more about that. So some of our customers, these logos on the slide you see, these are all commercial, paying actual customers. It's not marketing. These are not POCs. POCs is way bigger slide we cannot show yet. We'll show next year. So these are actual customers. Most of them are running large NVIDIA GPU clusters. One of them is running the largest AMD GPU cluster. Some customers are, these customers are hosting anywhere between 1,000 to 50,000 GPUs live, not theoretically live today. And all of them are trying to go and host 100,000 to million GPUs. And that requires a lot of complex networking. So since last time we presented here, roughly in 1 year from that, so we launched roughly 20 AI clusters, pure AI. So we had customers before AI, but I'm talking pure AI GPU clusters. And that happened to be 12% of neocloud market. Neocloud market is growing, of course. It's going to be way bigger than it is today. But today, that's 12%. And Our team, we had to grow our team. Most of you know that we're headquartered here in Santa Clara. But today we have offices across 6 countries because customers are all over the world, and the team grew 3 times. And the revenue happened, absolutely not important, but the revenue happened to grow 800% in just 1 year. And I'm not gonna talk about commercial side anymore. This is the last commercial slide. So let's talk tech with respect to AI GPU clusters. So this diagram is basically what everyone who's buying GPUs, this is literally what they are trying to achieve. They'll buy GPUs, they'll buy some networking hardware, some fancy expensive switches, they'll buy storage, they'll feed a lot of power, and they'll make a lot of money. That's how it works in theory, but in practice, there's a lot of nuances, especially around networking. And this session is for network engineers who are working for organizations where they are in charge of designing networks for their large GPU deployments, choosing solutions for their GPU and AI strategy. And we'll explain what are the nuances and what are some critical considerations we learned from our experience that you may want to pay attention. So this presentation is about bare necessities when it comes to network automation for your GPU AI cluster. And whether you consider building your own network automation or buy a technology, these are same considerations you need to think about. And among our customers, we have customers who are just starting their GPU cluster journey, who just deployed their first 1,000 GPUs. But we also have customers who are deploying their cluster number 8, and they are already 50,000 GPUs in their journey. And we even have customers who are very advanced. They developed their own in-house network automation technology, and they ended up transitioning to our technology. So I'll share more about all the learnings. So this diagram is a network diagram for a GPU cluster. And if you think this is complex, I have to spoil you, because this is smaller than the smallest customer that we work with. And even this tiny cluster, which has only 512 GPUs, it's like too small for a neocloud, or too small for like making real money out of GPUs. This tiny cluster alone has 1,200 links, 1,244 network links. And the big challenge with this GPU clusters is, unlike data centers, networking is not fire and forget kind of situation. Networking is very dynamic. You have to have multi-tenancy, and this means you have to have a way to dynamically reassign your GPU servers from one tenant to another tenant, dynamically reconfigure every network switch. And if some of you is thinking, what if I'm building a cluster for just one tenant, which is not uncommon case, but see, even when neocloud is building a single tenant cluster that has to be consumed by one tenant, sometimes it's 25 tenants, sometimes it's 500 tenants. But I'm picking this extreme case, one tenant. Seems to be like easy enough. But listen, to service one tenant, a neocloud needs to support multi-tenancy, because you need to have minimum 2 tenants in your infrastructure. In reality, you're gonna have more. But minimum 2 is hard requirement. Why? Because the way it works, you allocate some resources to your tenants, some GPU servers, and you as a neocloud, you're responsible for the infrastructure, responsible for power, and just like that, you are responsible for networking, the physical networking, configuration of the switches. And you are responsible for, like, let's say a GPU failed, you are responsible to replacing that GPU. And let's say you allocated the access to your tenant, and they are working and they are happy, and then a GPU failed somewhere. Now it's on you to replace that server. And to replace that server, you as a neocloud, you cannot have access to that server. That is your tenant server. Think about it. Can AWS access your data? I'm not saying technically. They are not allowed to access your data, right? Just like that, you as a neocloud are not allowed to access your tenant's server. So what happens, you need this other tenant. So you can take that server out from your main customer's tenant, put into your service tenant, and service that server, replace the GPU, reinstall the operating system, make sure it works. Then oftentimes uninstall the operating system and give it back to your tenant. So that simple requirement makes multi-tenancy hard requirement. And also, oftentimes when you're building a neocloud or just an AI factory, you just want to have this ability to share the infrastructure with lots of consumers. So multi-tenancy is a must. Now, how do you reconfigure 1,200 links dynamically on the fly without breaking things? And this is like super simple example. Real examples are much more complex. So look, AI networking, it's a cake of your own. Like maybe everyone heard of this Jensen's concept that AI is a cake of layers. Now networking itself has a cake of its own layers. It's not just leaf-spine networking. Leaf-spine network is just one part of it. Your GPU servers are also connected to east-west or backend network, which is usually rail optimized network, and it is responsible for GPU to GPU connectivity. And because it's rail optimized, we have a lot of switches. And sometimes it's not one network. Sometimes we have two backend networks. Sometimes we have four backend networks. These are called single plane, dual plane, and quad plane networks. Newer generations of GPUs, they require more performance from network, and we built quad plane networks. So this is a lot more networks. In addition to that, rack scale networking or scale up networking, what NVIDIA calls NVLink 72, that used to be a bus inside the server, but now this thing became a network of its own. Now you have additional 9 switches in each rack. So in each rack, to service a rack of GPU servers, you need few per each rack. You need few front-end switches, you need a ton of back-end switches, you need 9 MVL switches. That's like bare minimum. And over time, host networking is becoming also complex because the way workloads grow, there is this kind of growing need to also use DPUs in actual DPU mode, not in NIC mode, and I will talk about this, and I will show this also in the demo at the end. But essentially, there's this DPU thing sitting inside the server, which is kind of like additional switch inside the server, and that's a network of its own. That's additional fabric that needs care. Networking inside the host sometimes becomes challenging in some specific cases. I'll explain. And also, edge is becoming basically an important part of your front end, your north-south network, because your edge also needs to be dynamically reconfigurable and multi-tenant. So let's look at some examples from like real-life clusters. So like maybe someone is thinking, oh, maybe Alex is talking some theoretical, some future things, but it's not like that. I just picked numbers from few customers without exposing their names. There's a customer who's running small, what is considered small, 1,000 GPU cluster. They are a neocloud. They have 50 plus switches in their neocloud, and they have lots of tenants. So they do all this reconfiguration, this real live reconfiguration basically every day. And their GPUs are NVIDIA. Their switches are part NVIDIA, part Arista. It's one example. Another example, this customer has 18,000 GPU cluster, one cluster that has 18,000 GPUs. This is 256 racks of hardware, roughly 2,000 switches. The GPU architecture they are using that requires quad plane, meaning in their east-west network, they need 4 fabrics, 4 rail-optimized fabrics, all connecting to the same servers. So like on the back end, you can think this way. The GPUs looking towards backend fabric, each GPU has one physical port and then goes optical splitter and it connects to 4 different fabrics. And that applies to each and every of these 18,000 GPUs. And then they have rack scale networking, NVL72 in their case. So this cluster has 8 fabrics. They also use DPUs. Their tenant has this requirement that they need to use DPUs. So this cluster is using 8 fabrics. This is a real thing. It's not future. These are not plans. This is actual. Yeah.
Could you back up to the optical splitter?
Yeah.
I'm just curious what that means.
So when you have a multiple fabrics, see, initially the backend fabric was single rail optimized fabric, so like non-blocking, like every GPU can send 400 gigabits to every other GPU. Now, how to deliver more performance? So industry came up with this new hardware approach where they call quad plane or dual plane or quad plane. So quad plane means you're building 4 times of the same backend fabric. But on the server side, these servers are getting so dense, like you don't have room to put like a ton of plugs. So the way it works, it's still a single plug, but like deep inside it is using like a CDW or some kind of optical splitter that gives you multiple cables. So it's physically one plug, one SFP plug, and then you take different cables into different fabrics.
Okay. So it's using like CWDM?
Yeah. So yeah, along that line. So when you look from the server perspective, you will see like multiple NICs. So if your server has 4 GPUs, this kind of common form factor for this latest GPUs, 4 GPUs per server, you'll see 16 interfaces on the server side. Like you type ifconfig, you'll see 16 interfaces looking towards backend network only.
But it would be less speed then, right? Like you're splitting out like 800 gig into 4 200s.
Yeah.
Okay. All right.
Yeah.
Yeah. Okay. That's what I thought.
And there's example of this other cluster, 15,000 GPUs, which requires around 600 switches. It's single plane, so less switches. And it uses mix of Arista switches and some other Broadcom Sonic enabled switches and the AMD GPUs. So basically, what I'm trying to tell here is that all these different technologies are real. We are seeing these technologies in real deployments. And this is maybe also why that we are seeing this. There are a number of new switch manufacturing hardware companies, right? 3 hot startups right now, and they're building new switches. And people would say like, hey, we have, NVIDIA is the leader in, Ethernet switch shippings, and then there's Arista as a second, and then Cisco and these others. Why does industry need more switch vendors? This is why, because AI requires a lot more than just pure Ethernet, and NVLink is actively used, and the rest of the industry needs kind of equivalent for that scale-up networking. And we're also seeing DPUs actually being used. In the beginning, DPUs were there, but they were running in a NIC mode. So most GPU operators were not using DPUs, but we're seeing that this is changing. They are enabling DPUs, and they are willing to take advantage of DPUs, and I'll explain what that is. So in terms of hardware vendors, we are seeing, we're seeing a lot of NVIDIA switches, more than 73%. But we're also seeing some Arista switches, and we're seeing other Broadcom Sonic switches. At Netris, we're neutral. We work with any hardware where we see demand, and this is where we see the demand. We're in conversations with every network switch vendor that comes to your mind right now. Once there is demand, we will support them, but this is currently what demand is. There's also we're also seeing this trend of one AI cluster operator moving from, like, previously they were just they would stick to single hardware vendor, but now they're moving towards multiple. And roughly 26% of our customer base is using mix of more than, so they have more than one switch vendor in their clusters. So I mentioned this term NAAM, right? We like it. We invented it. We use it. We hope that industry will pick it up. So network automation, abstraction, and multi-tenancy. It's not just a bunch of words. This presentation explains what are some, we call bare necessities when you are building your AI cluster automation. And that actually describes what NAAM is. So it cannot just be, your old school fabric manager or your old school SDN. It needs to have this, these functionalities. I'll explain, and there's more I'll explain in following slides. So the same controller needs to be able to manage all these different fabrics: your front-end fabric, your back-end fabric, your out-of-band fabric. The controller needs to understand what is RoCE, RDMA over Converged Ethernet, and what is regular Ethernet. Same controller should also be able to understand what is InfiniBand, because InfiniBand is very common backend. Still, 40% of clusters are running on InfiniBand, and the rest are running on Ethernet across our customer base. Host networking, as I explained, also becoming a challenge for GPU cluster operators. So your same networking system should also handle host networking. In terms of DPUs, in some cases, there are some edge cases when you need to extend your VXLAN fabric all the way into host, either through DPUs or without DPUs. And also there are cases when you configure RoCE on your backend fabric, and you need to configure all the right things on the hosts, and it is also a challenge. And then edge, these isolations, these VXLANs, these VRFs that you configure, they need access to the internet. So you're essentially building a cloud provider, right? So you need to be able to provide this cloud-like network services. So I'll explain a little bit how we handle these things, how system is roughly architected under the hood. And let's start with Ethernet part. So NAAM vendor should absolutely be multi-vendor, right? Same functionality should work across multiple vendors. And although NVIDIA is like main hardware vendor, we see, like, the way market is today, most deployments are NVIDIA, but we are seeing other vendors. So these other vendors are also important for us to support. And the way our technology works, we have an agent that is sitting on top of the operating system. We have a ZTP server that can provision, install, uninstall, reinstall, upgrade, downgrade your switch operating system, because we're talking thousands of switches. These are like critical functions. And we have this agent sitting on top of the operating system, which means that as many switches you have, that many agents you are running. And if some hardware architecture doesn't allow for running an agent inside the switch, that's okay. We can run outside too. But most importantly, this agent system, it's a distributed system where you have lots of parallel processes, because this is the only way to make your network automation technology scalable. You cannot have like this old kind of Ansible approach where you have like all logic generated in one centralized place and kind of trying to make one centralized something tell thousands of nodes what to do. That doesn't scale, and that's not what we do. The way it works, our controller only has some high-level information, and I'll show you soon. And we have these agents that are distributed across your infrastructure, and each agent has this proprietary logic that knows how to translate your desires that are stored in the controller into actual, consistent, and validated configurations on every switch in orchestrated way. Similar to that, we work with DPUs. You know, NVIDIA has this technology called DPF, which is something that helps, which is basically a ZTP server for DPUs. It helps to, install operating system, but it doesn't help with the configuration, with the like everyday configuration changes. And NVIDIA has this framework called Doka, which is a library that sits inside the DPU, and it basically provides APIs and framework for something like Netris to provide configuration for DPUs. Again, it's a distributed system. We have our container sitting inside the DPU. We form EVP and BGP adjacencies between DPUs and your leaf switches, and that way DPU becomes like actual member of your switch fabric, and then we can provision VXLANs and VRFs, whatever is necessary across the network. We also need to integrate with InfiniBand, right? Because your backend fabric can be Ethernet, but it can be InfiniBand. And InfiniBand as a technology, it's more plug-and-play-ish technology, and there's not a ton of day zero work that we need to do, so we don't have a ZTP for InfiniBand because NVIDIA has this very nice controller called UFM, which takes care of day zero, day one, but it doesn't, that thing, UFM, it doesn't know about your multi-tenancy. So when you onboard, offboard, resize tenants, NVIDIA UFM doesn't know about that. So someone or something needs to be in synchronization. That's what we do. Our controller and NVIDIA's UFM controller, they are integrated, so we automatically discover the GUIDs and partition keys out of NVIDIA UFM, and when customer creates their tenants, we automatically push appropriate partition keys and associate right GUID. So we add that multi-tenancy functionality to InfiniBand. Then comes NVLink, which is NVIDIA's term for rack scale-up fabric. Now, NVLink used to be a bus inside the server connecting 8 GPUs. But today, it made its way out of servers into the rack, connecting 72 GPUs. And to do that, they added 9 switches. Not Ethernet switches, but like different kind of switches. And by the way, there are companies who are trying to solve the same problem through Ethernet, which can be a potential path forward. Anyways, MVL is something that is rack scale networking, 9 additional switches, and by default, all the 72 GPUs are talking to each other. And as a AI cloud provider, as neocloud, if you want to have this ability to split the rack, maybe you want a tenant, you want to have this ability to provide 4 GPUs to one tenant or 8 GPUs, right? How do you do this when 72 GPUs are always connected? So you need to have NVLink partitioning. That's what we do. We have integration with each rack. There's no rack-to-rack connectivity. Each rack is isolated 9-switch network of 72 nodes. So we have integration where our controller talks to each rack, learns everything about GPU IDs and existing partitions, and when you create tenants, not only our controller reconfigures your north, south, and Ethernet network, but also carves out isolation on your NVLink side of things. That way, we guarantee that your backend, your front end, your rack scale, everything is aligned with your isolation rules. So to summarize, NAAM, how NAAM is different from like SDNs or like intent-based networking. NAAM covers networking end-to-end, and by networking, we mean networking for AI use case, for neoclouds, for AI factories. NAAM is something that helps network engineers. You know, network engineers are very important for AI. It's not like AI is coming to take network engineers' jobs. It's not like that. AI needs network engineers. Network engineers make AI possible because AI needs hell lot of networking. So it's a tool for network engineers that helps them from day 0, day 1, and day 2. So they design their network through this tool, they simulate their networks, they deploy, they do validation of these massive fabrics, they automate troubleshooting of these massive fabrics on day 2, and they perform maintenance across these massive fabrics. And it also provides all the right APIs to others, to consumer side, because it's not, unlike traditional networking, it's not like network engineering is one camp and like, compute people are another camp. It doesn't work like that in AI. Everything needs to work together because there's no SDN. Compute folks cannot use software networking. Compute folks have to use physical networking, and your NAAM controller is the only thing that is connected to all these physical networks. It's the only thing that connects your desires, your intent, with like actual network engineering constructs. So
real quick, when you say it covers end-to-end, that includes, and you probably covered this in a slide that I'm forgetting, but that's front and back end networks as well. And
that includes north-south or front end, same term, east-west or back end, as many back-end networks as maybe 1, 2, or 4, whatever, maybe in the future 8, who knows, these AI people. MVL, edge networking, so your netting, your load balancing, because that thing too needs to be aware of your multi-tenancy, right? You can have overlapping IPs in your tenants. Your DPU networking, because it's like a switch in every server, and you have a lot more servers than switches. So if you have 2,000 switches in a network like that, you have roughly like 4,600 servers, that many DPUs. And all that needs to be orchestrated. And even NIC networking, sometimes there are some edge cases that networking on the host itself needs some additional help. So consider this very simple workflow, common kind of generalized workflow. Somewhere in any AI cluster, there is this PaaS IaaS layer. It can be commercial product coming from someone. It can be homegrown something. But there is some kind of system that is responsible for managing compute, servers, containers, virtualization. It may have customer-facing portal. It may have connection to billing system. Very important thing. It helps neoclouds make money. But this thing, unlike traditional networking, remember VMware had its own SDN. But that model, after acquisition of Nicira, I love Martin Casado, but it's just that technology is not in for AI. Because like these systems cannot use software networking because of an enormous amount of traffic. So they have to collaborate with something, your NAAM controller, that is in charge of your physical networking. And there has to be this API level collaboration or integration. So consider this. So these logos at the top, these are compute, orchestration, or platform companies, products. Some of them are open source. Many of them are commercial products. These are our partners. And we are grateful to NVIDIA for connecting us to these amazing partners and leading us the way to build very powerful partnership with all of them. Starting with NVIDIA Nico, which is this open source product that it's open source, recently became open source, and it's kind of gaining popularity. Or vCluster, Rafe, SpectroCloud, Red Hat, Mirantis, or CloudStack, which is another open source product. These are different technologies that neocloud builders are using to orchestrate their compute, install, uninstall, operating system, Kubernetes. Very important, but these things depend on networking, and these things have little to no network orchestration skills. And you know how marketing happens to technology, right? It's sometimes there is alignment, and oftentimes there is misalignment. And especially the bigger is the market, the more marketing misalignment you might see. And you may see terminology that is kind of saying that, oh, we do some kind of networking. So this presentation is kind of guide to network engineers to help them evaluate their neocloud orchestration stack. It's very important that you do networking right, and it's important to distinguish what network configuration can compute orchestrators do, and what kind of network orchestration you need from your NAAM platform. So your networking, because it's so complex, it needs to be really, really specialized. And I'm glad that our partners and us, we are in alignment on this. And it's been a lot of work for partners and for us to build all sorts of API integrations. So basically, we both can go to customer and say, hey, these companies, these products, and Netris as a NAAM work together. It's validated, it's tested by customers, by NVIDIA, by vendors, and this is kind of validated stack that you can buy and build further on top of it.